Hello, hello. Today we're going to be talking about radioisotope thermal generators. For some applications, such as deep space probes, long term power without any maintenance needs is required. This generally means you need very few or no moving parts. Solar power is not an option for deep space probes because they are too far from the sun. Conventional batteries lack sufficient power storage for long deployments. Current space probes have been in space for 30, 50 plus years. This led to the development of the radioisotope thermal generator, also known as the nuclear battery or RTG. To function, these do not use a turbine or any kind of reciprocating engine. For one thing, they don't generate any steam, and they don't want to. A critical reactor or a conventional nuclear reactor burns up fuel quickly. I mean, a normal reactor has its fuel replaced once a year or so. This produces a lot of heat, which is useful, but it can also overheat a system that's not good at displacing heat. Um, there is an exception to this. There are some pseudo RTGs that do have a critical chain reaction going on, but still use the primary method of converting heat to energy that all other RTGs use, which is the thermocouple. A thermocouple uses the Seebeck effect, which to generate a voltage based on the temperature difference between a hot side and a cold side of the thermocouple. RTGs use the heat from radioactive decay for the hot side. This is not a chain reaction, it is simply the natural decay of the radioisotope that's being used. This leads to the question of what isotope to use. As with many other applications of radiation, you have the trade off of half life versus the amount of radiation produced over a given amount of time. A longer half life means you get less power per hour or per day. So for RTGs, they commonly use plutonium 238, as this has an 87-year half-life, which is sort of a sweet spot for this application. Second consideration is decay products. In space, shielding is expensive to put into space because everything is expensive for any given mass. So you want something that is easy to shield. This means you want alpha particle emitters because alpha particles are easy to block, unlike gamma radiation or beta particles. Plutonium once again wins here, and the RTGs we use only need about 2.5 millimeters of shielding, and conveniently the heat exchange and thermocouples on the outside generally provide that shielding, so no additional shield, so no built-in, so no pure shielding is required. One concern is that there's power loss over time. Because the source decays, once you have less of your initial material, you get less heat out of it. The thermocouples also degrade over time. They're they're sort of a unexplored technology. After 29 years, the RTGs used in the Voyager missions would have fallen to about 80% due to decay alone, though when combined with the degradation of the thermocouples, they're more like 65% of their initial power. Some probes had delays before being launched, which reduced their initial power and had to have their mission profiles altered slightly. However, probes are designed around this. They are designed so they can shut off some instruments so that while initially they could run all their instruments, as their power available goes down, they can shut off some instruments as needed. You run one instrument, turn it off, run a second instrument, for example. Terrestrial usage is pretty limited. RTGs are bulky and do not provide a lot of power relative to what you would use as a person. probes are designed around these very small power outputs, but one of the three RTGs in a Voyager probe produces about 150 watts of power and weighs 40 kilograms. That's not enough power. That's about enough power to run a laptop. So enough to like run a house. You're like the weight of a car. Thermocouples also are just not very good at power generation. They're used in thermometers and quite successful there, but even outside of the nuclear battery application, thermocouples for power as a power source ends up being sort of quack ideas more so than actually providing mainline power. There are also nuclear proliferation concerns because plutonium and other potential fuel sources tend to be transuranics, which means that developing them, creating fuel for a RTG requires the same apparatus as creating nuclear fuel for bombs. That does not mean there are no terrestrial usage. There are inhospitable places on Earth where RTGs are valuable. This is mostly remote lighthouses in the Arctic and similar types of unmanned navigational aids. There's also a few spy stations out in the Arctic as well that run on similar principles. Essentially, something that they can be put out there in the Arctic where during the winter there's no sun for days at a time, and they need a power source that they can put out there and forget about. So, very similar in concept to the reason they use them for space probes. However, I think they're likely to remain so niche. They're the size constraints and just the general inefficiency remain, and they're just not they're not something that's going to be part of their actual power grid. They're mostly going to be useful in these kind of one-off situations. The nuclear proliferation concerns remain, and in fact, because of the controls on nuclear proliferation, the sources of plutonium or other transuranics are pretty limited. Uh, there's we're not making much more of it, and so RTGs have sort of a limited supply without restarting production. Those niche use cases will continue though, so I don't think they're going to totally go away anytime soon. Thanks for watching.